First guy I'd like to introduce is Chris Waite. Chris is with C-Corps. He's a member of our Certified Professionals program. He's a branch manager. He's a tech. He does a lot of field work. And Chris has done a lot of cold weather fusions. So welcome, Chris Waite. We also have Rick Ponder. We saw Rick's promo video there at the end that we were trying to run through in that opening video. Rick has got 30 plus years in the industry doing electrofusion installations and training throughout North America. Excited to have Rick with us today. And then of course we have our own Alan Ambler, professional engineer. Alan and Dan work closely with Jim Johnson to take Jim's base deck and prepare it for today. And then of course, Jim Johnston's our primary speaker today, Chief Technology Officer with McElroy Manufacturing. Next slide. So Jim, why don't you come on? So this is how you contact us, the various speakers today. We're also going to run this slide up at the end of the deck. Please know that this is a 75-minute session. We will be done at 15 minutes after the hour. So that's a total of 75 minutes, 65 minutes from now. Next slide. And I just want to reiterate, training is critical. We have two of the leading trainers that operate businesses as trainers. So Rick Ponder does electrofusion. McElroy has a university called McElroy University that does training of all the distributors. So Chris Waite, one of our speakers today, is with a distributor. So McElroy's team will go out and train all of the people that you buy product from on how to do fusions. And so Jim oversees all of that. And Dan, thanks for bringing that up on the screen. Just a quick survey of you all on the call today. We have over 350 of you on this call today. What best describes your knowledge? And Dan will run the answers to this in about 10 seconds. Jim, why don't you come on and tell us a little bit about yourself and what McElroy does?
So, sorry, I'm trying to get my survey off the screen. Thanks, Peter. My name's Jim Johnston. We at McElroy produce the largest product line of fusion equipment in the world. We make everything from half-inch CTS size equipment all the way up through 2-meter diameter fusion equipment in fully integrated and automated equipment, and sell throughout the globe. And as Peter said, McElroy University is one of our great offerings for training on butt fusion, sidewall fusion, socket fusion, and that goes beyond the distributor. We train operators all across the globe through that process as well, both in person and online. So we've got a very extensive process. McElroy is coming up on our 70th anniversary, and running very strong in that world today.
I got to say, Jim, it was a great move when you took inspector training full online. I've taken that class now, and I got to say hats off to you guys on that. Go ahead to the next slide, please. All right, before I turn it over to Jim, I want to bring on Alan Ambler, who we haven't introduced yet, and have Alan give us a couple slides on the background of polyethylene. Alan's a regular here in the webinar program, and we'll be hosting the next two webinars coming up in February that are on how you integrate polyethylene into the modern water system, and also the old standby HDPE 301. Alan Ambler.
Hey there, everybody. I'm so happy that Peter and Dan came and brought cold weather fusion. Of course, I am from Florida, so that's not going to work for me to be able to do this. And I'm so pleased that Jim Johnston, Rick Ponder, and Chris Waite, as well as Tarek Spear a little bit later on, will tell you exactly what it really means to be cold. But until we get to that time, we'll start back at the basics. I always love the opportunity to do so. And we'll start with what is polyethylene. So polyethylene is something that we talk about quite a bit, obviously, nonprofit promoting polyethylene's adoption in municipal water and wastewater systems. It's a semi-crystalline polymer that's also a thermoplastic. So with a thermoplastic, that means that can be repeatedly heated and cooled and heated and cooled. And that joint that is created from that thermoplastic or that melting process is as strong, if not stronger, than the actual pipe material itself. And so definitely don't hesitate to use that Q&A function and type questions. Richard's chomping at the bit to be able to answer your questions there. And we really love those live as we're continuing through these presentations. So advance to the next slide. What we'll see in polyethylene as this continues to go, it's kind of like chocolate. So as we continue to show you what happens, we are going to reform, melt that surface. In butt fusion, we'll push it up against and control the pressures to which we are putting those two surfaces together in that interface and allowing the molecules to run across that connection. And what we're doing in that scenario is allowing that integration of that polyethylene molecule to be able to run through that connection and continue to form that bond that we're looking for. That joint is exactly what we're looking for and wanting for it to be as strong, if not stronger, than the pipe material itself. Next slide. So what happens during this, if we'll just fast forward through the entire animation here, we're going to see those two surfaces at rest. And then when we start to heat that surface up, all of those chains will disentangle in that manner and then start to move across that surface. And all this is hydrogen and carbons as we're moving through in polyethylene. And then it gets between that boundary as we continue to move across. And then as it cools, then that will be as strong, if not stronger, than the pipe itself. So Jim, take it away.
All right, thanks, Alan. That's a great overview of what we have there and how this works. And so let's talk about that strength of fusion. As Alan said there, the fusion process itself is that melting of the joint and bringing together. And in this case, we're showing the butt fusion process itself coming together and that molten zone bringing the two ends of the pipe together and then reforming. And now we have a pipe that is as strong as the original pipe itself. And the steps to do a butt fusion are really fairly simple. You've got to make sure you do it right, but you clean and clamp the pipe. You face the ends to establish that clean parallel surface, align the ends, melt those pipes together, push them together by applying a force, and then hold them through the cooling time, very much to the analogy that Alan showed with the chocolate itself. That same process can happen to a degree also with electrofusion. And with that, I'm going to turn it over to Rick, if you'll come on and talk us through the process of electrofusion here, Rick.
Can you see me there? Didn't come on?
No, just do it without the video. If it doesn't
Okay.
work, we can hear you just fine.
Okay, obviously with the electrofusion, it's going to require an electrofusion fitting. And while it's a very robust fusion process, just as butt fusion is, it just utilizes a different methodology of getting there. So we have to have the fitting. We have to have clean peeled surfaces so we can get down to virgin material. And obviously the process will be using the fitting to melt the pipe, melt the fitting. It's going to swell. It's going to create the contact between the interfacial area between the pipe surface and the fitting. It's going to move between the cold zones, and then that's where the co-mingling of the process of the actual molecules are going to take place. And then it cools down, and you have a very robust fusion joint. We talked about doing the actual fusion. The methodology is with the electrofusion fitting. It has two areas. We have a fusion zone, the area where we have the wires, and the area where we don't have the wires, which are the cold zones. And as these fusion zones heat up and it begins to expand and move out to the cold zone, it dams up, builds the interfacial pressure, and then the actual fusion takes place, basically in the simplest form there. It's going to utilize a electrofusion processor. We also call that a control box. On all the electrofusion fittings, we have barcodes that allows us to be kind of a universal way of inputting the fusion data. By scanning the barcode, the processor will recognize the fusion parameters that each fitting has, and it'll put it into the process and into the processor after you attach the leads and scan the barcode. And we just want to make sure that when you're going through this process, that the data that you have on the label is being confirmed with what you have on the screen. And then after you hit the start button, things are good to go. And that's anything else there.
That's it, Rick.
Okay.
Thank you very much.
You bet.
All right, with that, we're going to talk about, as the title of the presentation today is cold weather fusion, but we're going to talk about inclement weather. And while our focus today is going to be on inclement, or it is going to be really very heavily focused on cold weather, this really applies to any kind of inclement weather that you may run into, situations where there could be contamination, water, other ingress into the fusion area, whether it's electrofusion, butt fusion. Doesn't really matter what your process is. You shouldn't be doing any kind of pipe fitting of any kind in without some sort of protection. So we're going to talk about that in terms of that generic weather condition that's unsafe or undesirable. It can come from rain, snow, sleet, hail, high winds, extreme temperatures. We'll talk about situations in Australia this past year where we saw temperatures approaching 130 degrees plus out in the outback. So take those into account as we move forward. With that, we always talk about safety. And Chris, you've been on job sites. You want to talk a little bit about how safety impacts any job site that we're talking about? Well,
Okay.
there's Chris.
Sorry about that. Forgot to unmute my mic there. So obviously safety is going to be your number one priority on any job site. Polyethylene, when you're out there fusing it, doesn't have any other unique safety considerations comparative to any other pipe. The big thing I will tell you is in the cold and dragging and stuff like that on these job sites that you will see a lot of kinetic energy built up in this pipe. The colder it is, the stiffer it gets, and you will get into a safety aspect of that. Other than that, I mean, it's really your safety priority is going to be your priority number one, but at the end of it all, you're going to be no different than any other type of pipe.
Did my slides go haywire here?
Yes, sir.
All right. Sorry, I have had a little bit of a failure. Hold a moment, please. So Chris, you were saying that safety really doesn't matter what kind of job site you're on, right? That it is whatever system you're doing, wherever you are, you should be following your safety protocols and handling that. That's even more important with cold weather.
Yes, sir. The pipe is going to be very, it's going to be a lot stiffer in cold weather. It's going to not take the impact resistance. When you're roping pipe around a corner and stuff like that in the wintertime, that pipe is going to carry a lot more kinetic energy throughout it because it is stiffer. It's not closer to a molten material at that point.
Chris, what are the three top ways a guy's going to get hurt on a job site with a polyethylene pipe present?
Loading and unloading is probably going to be the number one situation out there. See more people when you're loading and unloading pipe. You've got to be sure that first off, you're over the length of the pipe away from the end of it while you're loading and unloading it. Second off, you're not on the backside of a truck. I've seen more people in the field, drivers that aren't experienced when they're hauling this. They'll walk around the backside of the truck and you will see a forklift come in. They will go to grab a bundle of pipe and off the backside goes a stick or two of pipe or even a whole bundle of pipe. That's one of the biggest safety concerns out there. And then when you're dragging this pipe, remember that it has that stored kinetic energy in it. So when it comes around the corner, that tail, especially at the end, that tail is going to whip out. Them are the two primary safety concerns I see in the field.
Are there any concerns with fusion operations?
Yes, various pinch points. You don't want to put your fingers in anywhere without making sure the machine is either disabled or controls are locked out. Macro has done a very good job, especially on their larger diameter fusion equipment, to where you can shut that machine down where there's no hydraulic movement while you reach in to clean out shavings. You don't bump a control or anything to that effect.
Thank you.
Are you seeing my slides back?
Yeah, you're good.
Okay. All right. Sorry for everybody. As we all know, technology, some days is our friend and some days it's a challenge. So as we talk about this, one of the things that's really key with polyethylene is that one of the great pieces of polyethylene and the advantages is that it can freeze solid without damage. So you've got a huge advantage here versus other entrenched materials that are out there that will just shatter as the pipe expands. That polyethylene pipe has enough flexibility in it that can freeze solid on the inside. So that's a great behavioral characteristics and one of the great advantages, especially in a cold weather situation. Even when you've got situations where this pipe is not buried below the freeze line, you've got the capability that it can survive that situation. And it can happen. It can do that without damage at all. We've also got some really good slides up here. This pipe that you're seeing on the line is actually insulated pipe. So there is a carrier pipe in the middle where you see the water flowing out. And around that is an insulation layer and another layer of polyethylene over the top of that. So you can actually have insulated pipe that further keeps that water flowing, not just freezing and allowing it to be able to manage that freeze, but continuing to move. Here's some other situations where you see some of that insulated pipe. And when we go to join that pipe, whether it's by butt fusion or electrofusion, that insulation area is stripped back from the end of the carrier pipe, and either your electrofusion or butt fusion are done there. And then typically a wrap, many times a wrap will come back over that exposed area and re-insulate that component. But now you have a completely insulated system throughout your process. One of the other features that you'll always see is use the tools that are available to you to help align the pipe. The beauty of polyethylene pipe systems is whether you're using coiled pipe or stick pipe, you can have very, very long runs of pipe and that capability. And you want to use that, use pipe stands, lifts, rollers, other components to keep that material off of the ground so it doesn't get scratched. But also to help you move the pipe into the machine, move the pipe out of the machine, minimize that friction piece. And Chris, I'm sure you've got some comments relative to the equipment that's available out there, why it's important.
Yes, sir. So the biggest key in this whole situation and these productivity tools that Macroy offers is setting your job site up correctly. If you set that job site up correctly and you use the tools properly, the way they're intended to be used, you will, not only is it going to increase your production, even in cold or extremely hot weather, but it's going to make your job site much safer. When you're out there with equipment, you're just trying to hold up on the pipe and fuse it and drag it and not use the tools properly. It makes your job site much less productive, and it also makes it much more unsafe than it would be if you just set it up, take the time to set it up and do it properly.
Yeah, so got a couple of examples of some installations that are really key or really great examples of both cold weather applications and cold weather ultimate uses. The West Fork Upper Battle Creek diversion. This was really a fantastic project in the state of Alaska. It was put in at the Bradley Lake Hydroelectric Dam, which covers a huge portion of southern Alaska, that hydroelectric dam. And the reservoir that feeds that hydroelectric dam was running low, and there is a glacier stream that was rerouted to be able to continue that glacier stream on its current path, but at certain times to be able to be diverted to refill the reservoir. So it was 2.5 miles of 63-inch DR-17. For those of you that are not familiar with that, DR-17, now it's roughly 3.7-inch wall thickness material. This was built up literally the side of a mountain going up a glacier. You can see the McElroy Talon going up that grade. They were fusing on that side of that hill up to an 18% grade. This was one of the toughest projects that was out there. This machine has ever seen. This machine will do up to 2-meter diameter. This pipeline was the road was built, and then it was buried right into the side of the road, and then the road was taken back out at the end of this project because it's on a national park. So very cold situation, obviously in Alaska. But a great application for polyethylene, can be a long-term solution to maintain that hydroelectric dam up in that area, and really a fantastic solution for HDPE. I was on this job site. You can actually see the grizzly bear in that bottom left picture, not a grizzly bear, but a black bear, coming and inspecting the pipeline. They had to chase bears off the job site quite a few times. And in the bottom right picture, you can see that amount of incline that goes up the hill, and the tie-in here at the bottom as they're doing sections as they go up this hill. So Rick, if you would come back on and let's talk a little bit about normal operating temperatures. How do you process, and how do you do things? What's normal?
When we talk about normal operating temperatures, basically what we're talking about is the ambient operating temperatures when you're installing electrofusion fittings, where you don't have to make any changes to the standard fusion times or procedures. And electrofusion, that tends to range between 14 degrees and 114 degrees. Now, it can be fused colder, it can be fused hotter, but in those instances, we basically would like to be called to find out what temperature range, just in the event we may need to modify fusion times or something like that.
Yeah, and on the butt fusion side, the standard basically says you should not be fusing below 5 degrees Fahrenheit. There's a lot of things that go there, and we're going to talk a little bit as we get further into this. You're going to hear me say a few times. Chris, come on as well.
Yes, sir.
Me talk. Go ahead.
So to touch base on that statement that you just made, it doesn't mean that you can't fuse below 5 degrees Fahrenheit. It's not recommended to fuse below 5 degrees Fahrenheit without precautionary measures being taken. So it doesn't mean all of us up north have to shut our jobs down when it gets cold outside. So keep that in mind when Jim's talking about cold weather fusion. Yeah,
and exactly, because I know of a job in northern Japan that was doing fusions where the outside temperature was -47. So it's not about the outside temperature, and we're going to talk more about this as we go through the day today. It's about changing the environment. When the outside temperature is below that point, you need to change the environment. You don't change your procedures, whether it's electrofusion or butt fusion, but change the environment, put it into a container, do some other components. So we'll talk a little bit about that a little bit more. Alan, if you're going to come on, talk a little bit about where we are with temperatures and operating ranges.
Microphone. All right. Looks like we're having an issue with Alan.
So
go ahead, Jim.
The material itself, polyethylene itself, has a service temperature range ranging from -40 degrees to, which is roughly -40 degrees Celsius, roughly, also to 140 degrees. That's your operating temperature. for the material in process. You're going to have some applications where you're going to be hotter than that, but you're going to lower the pressure. The glass transition temperature, meaning when is this material going to fracture if I hit it, is minus 130 degrees Fahrenheit. Hopefully none of us ever have to see minus 130 degrees Fahrenheit. But that means it's much more flexible. It has much more capability. If we were to look at some of the other amorphous polymers, which are not HDPEs, some of the other plastics that are out there, their brittle temperature, that glass transition, meaning where they become brittle to impact, happens at 220 degrees Fahrenheit. So they're brittle just sitting on the ground. So again, one of the other great advantages of using HDPE. Thermal effects themselves, we actually see that polyethylene has a very strong thermal expansion rate. The rule of thumb is a very easy piece to use here, which is 1/10/100, meaning that it will contract or expand at a rate of 1 inch per 10 degrees Fahrenheit per 100 feet of section. Now that's unconstrained. It means if it's just laying on the ground, it will expand or contract at that 1/10/100 piece, but it takes a very much smaller force to restrain that, because the force of that expansion is much less than carbon steel or stainless. If you look at
hit the animation on that. It'll show it at the bottom.
oh, there it is.
you go.
Okay, sorry. So a 2-inch Schedule 40 pipe in its contraction will actually have almost 8,000 pounds of force in its contraction. However, that longer expansion in a 2-inch HDPE pipe will be 321 pounds, because the elastic modulus is so much smaller than those other materials. So your restraint requirements on those larger pieces is so much greater. There's Alan. Do you want to add in here, Alan?
Oh, yes. Sorry for that. One of the key things when we're looking at HDPE in a cold environment, if you want to go to the video on the next slide, it'll kind of bring a synopsis to it all here. As that pipe just gets colder, then it just requires more force to be able to manipulate it, move it, and things of that nature. So you still have all of the behaviors that are inherent with HDPE, with durability, flexibility, and all those things. We just now need to be able to manage that pipe in the cold environment with additional force. That's it in a nutshell.
So guys, if I could summarize handling polyethylene in a cold environment, I would say when it's colder, it's more pressure capable, but it's also stiffer and it's harder to handle. Would you agree?
It is harder to handle than well, I wouldn't say it's harder to handle. It is know what you're dealing with and take your time. So coiled pipe, you just need to go slower than you would if it were 80 degrees outside.
Okay. Chris, how would you characterize it?
I would characterize it all like Jim there, but coiled pipe is huge, and that's where you see most of your injuries come in the polyethylene market. I've seen guys that this prime video that you guys just played on this presentation, that guy walking along that spool out trailer is not the smartest place to be. You would want to be in front of that trailer, because if that pipe were to by chance break, that tail's coming around. That pipe has that memory and it wants to come around and recoil itself back up. So that's
just like a clock spring. It's just like a clock spring. It's going to roll right back up.
Thanks, fellas.
Okay, Rick, do you want to come on and talk a little bit about where we are with getting to equilibrium?
Yeah, I mean, since we know that temperature does have an effect on the polyethylene pipe and fittings dimensions, and we also know that electrofusion fittings are manufactured to really tight ASTM dimensional requirements, we really have to make sure that both the pipe and the fitting are acclimated to the same temperature. In other words, if both the pipe and the fitting are the same temperature, everything's going to go together fine. The interfacial gap's is not going to be too large that it can't be filled as the plastic melts and expands. When you have a pipe that's at a higher temperature and a fitting it's a lower temperature, the pipe could be larger than the fitting and it may not go into the fitting easily or at all. If the pipe is colder than the actual fitting, then it's going to be smaller, then it will slip in easily, yeah, but the gap may be too large for the fitting to actually heat up and expand and close the interfacial gap like you need to do to get a good fusion.
Great, Rick. Thank you. So there are considerations to come into this. And again, these are a little bit like the safety considerations when you're dealing with cold weather world, whatever pipe system you're dealing with, you're going to have these kinds of things. And so these are just the specifics that we need to know. Relative to the equipment on the butt fusion side, you've got hydraulics that are involved here, and cold weather temperatures and hydraulics. You need to make sure that you're choosing the appropriate hydraulic fluid for the application that you've got. If you're in a very, very cold situation and you're using a high temperature hydraulic fluid, it can get really maple syrupy, and that changes your characteristics and affects your pump. It does a lot of other things. So you want to make sure that your equipment is set up to maintain that. And as you look at the chart, this comes from, in fact, our McElroy recommended hydraulic fluid. There's a pretty broad range of operating temperatures for hydraulic fluids, but if you are working above the Arctic Circle, you're going to have some specifics where you want to be really close with that. Chris, I think you even have some situations sometime in Wyoming where it can get pretty darn cold up there.
Absolutely, and making sure that you have the proper hydraulic fluid in your equipment based off of your temperature is huge. I've had machines come up that we've shipped them. Obviously, we have locations all over the United States, but you ship them up from down south and they've got that molasses type hydraulic oil in there, and you fire it up here and it starts blowing oil coolers out or blowing hoses because it'll back pressure that system, because it's like pumping honey. So be sure that you're really selecting the right oil and checking all of that before you fire that machine up and tear things up.
Yeah,
So-
and that's the same for the generators as well, right?
Yeah.
Absolutely.
So Chris, while Jim goes to the next slide, how long does it take if I've got a McElroy fusion machine out in the cold and I bring it inside a tent? How long does it take that hydraulic fluid to warm up so I can safely operate that McElroy machine?
So it's really going to be based off, obviously, ambient temperature, what your conditions are inside the tent. But you got to think about all this. Their hydraulic tanks are all iron. That you can walk up with that and you can put a heater on that iron tank, and the surface of the iron is going to feel warm. It's no different than boiling water. You touch the pan's going to be hot, but the material inside the pan, it takes longer for that to heat up. So you really, it's in all McElroy fusion equipment, generally speaking, they have a temperature gauge on that hydraulic tank. So make sure that that's in the operating range temperature wise before you fire the machine up.
Right. So generators, same situations. You got cold weather, altitudes, you've got other components. You want to make sure that they have the right hydraulic fluid in them, but they're also going to be affected. The output voltage is going to be affected by that temperature and their ability to run. So we got to be careful with that, whether it's electrofusion or operating an electric only fusion machine or butt fusion machine, correct?
Yeah, so the other situation is remember, temperature derates your generator. It's not going to perform at its peak. I see a lot of guys that will ultimately, and gals out there, that they go look at a generator and it says it's 7,500 watts. Well, I looked at my situation there of that's what it says my power requirement is, but they're not reading the fine print on that generator of elevation changes and how it derates, and that's peak wattage when it fires up. So we want to be sure that we're taking care of that. McElroy's been really good at putting out the wattage requirements of what's going on all their heaters and all their fusion equipment. So be sure you're protecting everything. The heater, always, if you can, go to the next size up generator to make sure that you're overrated rather than underrated.
And all the electrofusion manufacturers do that. Rick, I know that you guys have very specific requirements and specify what the minimum requirements are for firing all those pieces as well.
Yeah, we do.
All right. I'm going to take the next couple of slides here, fellas. We've got, for our audience, we've got half an hour left, and we've got some of the best content to come. We're very thankful for ASTM and the Plastics Pipe Institute for giving us a lot of guidance. In fact, PPI produced last year a cold weather technical note, or an MAB document. It's MAB number 08. And the Municipal Advisory Board is a subset of the Plastics Pipe Institute, specifically their municipal and industrial division, managed by the preeminent Camille Rubiez, who does a fantastic job. And anyway, so we got the idea for doing this deck because of this great document that they produced. And they set out about 10 different things that are good to know, like really basic stuff. Hey, if you're going to do a fusion, remove the snow and ice from the fusion zone. Don't drop the pipe, duh. But you know what? The reason I say it's a little bit harder to manage is because it's cold. You've got gloves on. Your machinery doesn't operate as well as you may expect it to. Using closures. You know, we talk about, yeah, let's fuse at 0 degrees, but guess what? Every experienced individual that's doing fusion operations below 32 either has a tent or wishes they had one. So in fact, the MAB came out, and I think, Jim, correct me if I'm wrong, they said, we don't really want you fusing under 32F or 0C unless you have taken the necessary precautions that we will spend time on. Also, other key elements are shield the fusion area with a shelter or a tent. Make sure that the ID and the OD have no moisture. A lot of people that like to hate on us say, oh, you've got to have a dry fusion zone. We can just put our pipe together when it's cold and wet. You're right. But do you want a joint that's going to last hundreds of years? Then go with polyethylene. Then there's this whole thing that I can't wait to hear Chris and Jim talk about, of preheating the pipe, whether you use forced air or you use heating blankets. I've seen that a couple times in the field, but those guys know a whole lot more about it than I do. But we've established with this team some golden rules. The first golden rule is be patient. Accept the fact that it's cold. Accept the fact that the weather isn't any good and that you have decided to do fusion even though it's raining or cold or foggy or it's sleeting. This is the one I love. When I was taking my fusion classes from Jim and his colleagues at McElroy down in Tulsa, they said to me, change the conditions, not the procedure. Jim, tell us about that.
So it's really the standard procedure that's out there is ASTM 2620. It prescribes all the components and all of the functions that you do, heat times, pressures, all of those pieces. And those don't change with the temperature. So what you want to do is make sure that you change your conditions so that you follow that procedure. So we're not going to change the procedure. We're not going to do anything different. We're not going to crank up heater temperatures. We're going to follow that procedure, but we're going to make sure that all of the materials work in the way that they're supposed to work.
Well, Jim, that's why I'm so glad at the beginning that you talked about what the procedures were. Clean it, shave it, heat it, fuse it. And Rick on electrofusion, those are the basics. So whether there's snow or wind, doesn't matter. We're going to stick to the same procedure. Go ahead, Chris.
You're on mute.
I see a lot of these guys on the change the conditions, not the procedure. Hundreds of times I've had guys come back. Oh, we crank the heater up to 500 degrees just because it helps heat it faster when the pipe's cold. And that is the biggest no-no that you can do out there. That changes the properties of the HDPE. So people keep that in mind when you're looking across all of this, to make sure that you are changing the conditions and not the procedure. It is huge and it will affect your job tremendously.
And be patient. I mean, we're not talking about this as changing your time by 100% or even 50%. It just means it is going to slow you down a little bit as you heat a cold piece of pipe. But it's assuring that you're doing the things correctly. It's just
Exactly.
ensuring that joint going forward. It is not a significant amount of time, and those shortcuts are detrimental in the long
But
term.
it really, after all my years of experience in the field, Jim, it's going to take you longer to heat that pipe and develop your bead, but it's also going to cool down somewhat quicker. There is
That's exactly right. There's a trade-off. Yes.
amount of time that you have to let it cool down, but it's also that procedure kind of speeds up in the wintertime when the pipe is cold, because it is going to cool down faster.
It does do that.
So I see questions are starting to heat up. We love those questions. Keep them coming. And the next slide, Jim, I'd like to ask you guys, and I don't recall ever seeing this in a procedure. How far back do I have to clean off the moisture in the snow from the point at which I'm doing facing operations?
My short answer would be is you want to clean back past or at least equivalent to the first jaw. But you want to be at several inches away from the face-off zone, so that you don't, if there's moisture inside the pipe or on top of the pipe, that it doesn't follow or leak down the pipe and come back into the situation. Good practice is to clean the whole section that's going in the machine.
Yeah, Chris, you want to add anything?
Anything that comes in contact with the machine, you want to clean that snow and ice and dirt off of it. Not only is that going to keep your serrations clean, and it's going to grip your pipe better, especially as this pipe's contracting in the cold. Them jaws have to close down just a little bit more to hold it in there. So anything that's going to be in contact with the machine, I recommend cleaning off and having a nice clean surface.
All right, so you're going past, Chris, you're going past the second jaw.
Absolutely. I'm going all the way outside the fusion machine.
That way you're not
Some
getting
of these may be 4 feet, some of them may be 2.
Yeah, you're not getting any contamination on the machine that gets pulled in with the next joint.
So this next slide, I mean, I love this one. Inspect the pipe for damage. Okay, good. Inspect it. Cut out any compromised areas. The cool thing is with that jagged edge there, you can cut that out. If it's greater than 10% of the pipe wall, you cut it out, face, fuse. This next image I got from Richard Kalasa. That guy, he ended up getting a drunk driving ticket. You see his tire there on the polyethylene pipe. And in fact, that polyethylene pipe was not damaged. But you had to inspect it to make sure that it was not. So we also say, hey, don't drop the pipe, particularly when it's cold. You want to place your polyethylene pipe. So we can't say for certain that the pipe isn't going to get damaged if you drop it from a height and it's super cold. In fact, Richard Kalasa tells a story about a horizontal directional drill he did, that some car hit his pipe, they pulled it in, and of course they found a crack right at the apex of the drill at the bottom. And it was 40 degrees out, 40 degrees below zero when that car impacted that pipe. So you can damage the polyethylene pipe. So we do like to talk about protecting that fusion zone. What a great way to do it is use a structure, a 20-foot or a 40-foot trailer, or buy a tent and get sides on it. But don't use excessive heat, whether it's a blanket or whether it's forced air. And we have a guideline for how much heat you can use. I love this next one because we talk about shielding the fusion zone, but here we have two great, Chris Waite talks about productivity tools. Well, here are two great ones. One, we have the Quick Camp, which is McElroy's version of a tent. And the second is, Jim, what's the specific brand name of the product there on the previous slide on the right that holds is that the Polyhorse that holds that polyethylene pipe?
Yeah, that is the Polyhorse, that big rack that feeds into the Quick Camp. It's called the Polyhorse. Yes.
So that's like one guy, once he gets it loaded, one guy can do all that?
Absolutely, yes. So there is powered rollers on the front edge of that. So an entire bundle of pipe can be stacked and set, and then you've just got a system that feeds directly into the machine using a powered roller. So one person can do that. You eliminate a lot of material handling and other things on that job site by just bringing in those full bundles and stringing that pipe out.
Yeah.
Using coal.
Fantastic solution. Then we have just a couple other images here. A lot of guys will use their own tents. They'll make up their own deal and their own version of the side protection. Don't forget, you have to have exhaust for that McElroy machine. So it's a fantastic way to control your environment. Don't change the procedure, change the conditions. Now we're up to Alberta. Who wants to handle telling this Alberta story? Jim, why don't you take it?
Yeah, I can take it. So this was a wastewater system up in Alberta, Canada. It was 10 kilometers long, supporting a wastewater system for a very large population growth up in that area. It was horizontal directional drill and open cut. Nib Development was the primary contractor on that. They had previously tried to use just tents, but they found that in their conditions they were having troubles with just tents, and they ended up buying a quick camp system with Polyhorse, that big rack system that you see there, and taking them the ability to set and load all of this piping into their system very quickly and easily. And it's the inside of this container is temperature controlled, so the operator was able to do this in a temperature controlled environment, controlled not only the fusion process, but you're also protecting the operator. Remember, if your operator's not able to perform at minus 40 degrees, so even above and beyond what we're talking about with the equipment, you want to protect your operator. In this case, this container opens up, actually has space for office or storage even, and really drove home a really great opportunity for them. And they finished that job well ahead of their other schedule because they were able to protect the operation, protect the operator, and actually run 24 hours a day through that process. So the other thing we want to talk about and this is in general terms, plug the ends of your pipe. This is an opportunity to, one, keep the interior of your pipe clean and clear, but it also prevents wind from flowing down the end of that pipe. You have a giant Venturi tube. If you have an open end there that's blowing cold air or dust or other contaminants into your fusion zone. So if you cap the end of your pipe, we've seen everything from the caps that you see here in this location up to just simple trash bags and other pieces, but just cap the ends of that pipe and it'll help you with your cleanliness, help you with your overall flow of material.
Well, keep in mind on that, Jim, when they're capping the end of the pipe, you want to cap that pipe when it gets to the job site.
Yes.
Don't wait until right the day you're going to fuse it, because at that point you're already full of ice and snow and critters that are hiding from the cold elements and stuff like that. Yep. So as that pipe's showing up, stick your bag over the end or whatever you're going to use. Do that when the pipe shows up on location, because when it comes from the factory, it's as clean as it's going to get inside.
Yep. And the last thing you want to happen is have a skunk squirt in the middle of your pipe during the middle of a fusion. That'll ruin your day.
Hey, Jim, just a comment on that. Sorry, I'm not supposed to be involved here, but for that, you can request if it's a isolated a job site and it's way out in the boonies or whatever, we can cap that pipe for you. There is an additional little cost associated with that, but it's marginal. It's not that much, but you can request that and we can pre-cap it for you.
And you're saying,
yeah, from the manufacturer standpoint, but we need to know that prior to the order. We won't do it after the fact because it's just not efficient. It's much more efficient to cap in line after the pipe has been tested, and it's a lot easier for us that way. So
great, Richard. Thank you for that. So we talked about one of the pieces that one of the steps that are ongoing here is ensure that equipment is free of ice and snow. This is also that dirt aspect. So when we talk about inclement weather, don't let snow, ice, moisture, water, dirt get on your machine. Clean it up as much as you can, because when I finish this fusion and pull that pipe through, I'm dragging snow and ice all the way through there. Ensure that the ID and the OD of the pipe are clear of moisture. That's not just visible snow, but moisture. So you don't want that water getting into the joint, either in the ID or the OD. It's a simple process. Just clean it off before you put it into the machine and make sure that you've got good, clean capabilities. So use portable heaters, and there are a ton of choices out there. And Chris, you might talk about some of them that you've seen out in the field. We want to make sure that you're using either indirect heat. If you're using a flamed heater, you don't want to put flame on polyethylene. But salamanders are one of those big ones that we see used quite a bit, and can use indirect heat off of that through a venting system or a tube to run over into the pipe or onto the pipe or into the tent to maintain that temperature and raise the temperature inside the heating zone.
Yeah, so the biggest ones that I see out there, I mean, you get into infrared heaters. The salamanders are great. They make flameless rig heaters. The flameless rig heaters are probably about the best because they put off the most heat. You can heat it up quicker. With tinting the end of the bundles of pipe, you can get that stuff up to temperature in a nice fusion range a lot quicker. So some of the heating blankets and stuff like that, they're going to take a lot of time, because once you wrap it on there, then the thermostat kicks in and stuff like that. Them are great for electrofusion. I don't necessarily recommend them for butt fusion when you're out there, because they are time suckers at that point.
So one of the options as we get into this is to preheat that pipe. So as Rick talked about for the electrofusion, where you want to have stability of pipe, you want to make sure that you're going to be bringing this pipe up against a heater that's 450 degrees, but you don't want a huge shock to that heater, because you're still trying to melt the ends of that pipe. So it helps to preheat that pipe. Try to do that in an insulated area. We see a lot of pipe being maintained in a tent by itself. You don't want to heat it to greater than 120 degrees, just because you're starting to get into zones where you don't want to mess with the sag of the pipe or any other components. And use multiple heaters where you can. Reels and stick pipes can be tinted with tarps and heated with warm air from an indirect fired heater, as Chris was talking about. You can have that prepped and ready. It helps your pipe be cleaner before it goes into the machine. So there's a lot of things you can have on site ready to go, and be ready to go into that tent with a piece of pipe that's ready to be fused.
So Jim, 30% of the folks on the call today consider themselves advanced. Where does heating and preheating and cold weather operations play with the whole McElroy accelerated cooling, optimized cooling?
So optimized cooling, so heating and preheating, optimized cooling only applies to the cooling side of this. So it does not affect the heating side. So heating and preheating are one of those things where it's still be patient, follow the procedure, take advantage of those pieces. So there's no change by using optimized cooling in the heating or preheating stage of this, because you're
Okay,
still
so
going to have
the software in the DL7 permits us to use optimized cooling, even though we're fusing in a tent and things are cold.
even though we're fusing, we are taking into account the ambient temperature and the temperature of the pipe to calculate the cooling time. But the heat time, the bead size, all of those components that are part of the procedure do not change.
Great, thank you.
Again,
So that same thing, just to touch base on that a little bit, it's going to ask you on the data logger for the optimized cooling what your pipe temperature is. Now, if you're preheating that pipe all the way up to the maximum of 120 degrees, that is going to affect your cool down time on optimized cooling. So keep that in mind. You want to get that pipe up hot enough where it will still fuse properly, but you don't want to get it so hot that it's going to increase that time for you if you're trying to run optimized cooling.
So we have a guy just asked a great question. He goes, okay, cold, what about hot? He's seen pipe as hot as 200 F. We're not supposed to preheat above 120. So what is he supposed to do when the pipe already starts super hot?
So when it starts super hot, in those cases, you want to have some protection there. Black pipe is going to be a black body that absorbs heat. Your best choice is to try and protect that with a tarp or other things. But it is not one of those where you can't preheat. It's not a prohibition to have the pipe greater than 120 degrees. It's just a best practice to not try and go any hotter than that in the cold weather situation. And we've seen 160, 170 in heat in sun loaded pipe. I've never seen 200. That's pretty extreme, and that is going to extend your cool time quite a bit, because you're up into a very almost not at a softening point, but you're getting close to a point where, from your cooling standpoint and your ability to handle that pipe, you're going to have to slow down and really allow that pipe to cool for a long time, or protect that joint to allow it to cool for a long time.
Great. Good explanation, guys. We're just got a couple slides left in the main deck. And
Yep.
then, because I know we're at the top of the hour and we typically lose a few folks at the top of the hour, we're going to bring Tariq on to talk about his experience in Alaska in about 5 minutes. So from a standpoint of managing your time, there we go. Take it away, Jim.
Okay, so last couple of slides here as we bang through. Keep your heater in its insulated bag so that it is maintaining itself. It's just like your operator. If you're out there running this machine, you want to stay in your jacket so you don't get cold. Keep your heater in its jacket so it doesn't get cold. Summary overall: don't drop the pipe. Provide adequate enclosures. This is good for you. It's good for the operator. It's good for the process. We want to make sure that we have the capabilities to protect that fusion process, electrofusion or butt fusion. Make sure that it's clean, it's dry, it's protecting the operator. Use tents and warm air wherever possible. Protect the fusion zone. Use space heaters where you can. Preheat the pipe where you can. Keep the heating tool in an insulated container. Understand your thermal effects. That could be cold, that could be hot, just like we just talked about. You're going to have pieces there. So just know your extremes. And when we're talking about these, we are talking about extremes on these sides. Provide the enclosures, protect the fusion zone, keep it in the heating container. In windy situations, cap the pipes, protect the fusion zone, provide enclosures, keep the heater in an insulated container. These are all pretty rote over and over pieces. In precipitation, whether that's rain, snow, sleet, hail, hopefully you're in a container, you're in a protected area. If it's hailing, remove and clean that ice and melted pipe or snow from the pipe. Make sure it's clean and free of moisture. Provide enclosures, protect the fusion zone, clear the ID and the OD, and keep the heating tool in its insulated container. And with that, we will have, this is our contact information. I want to thank again Rick and Chris and Peter and Alan and Richard for joining in here and being ahead of us, and everybody else that was involved today. Dan, thank you for kicking us off, and Peter, thanks for having us on today.
You bet, Jim. Great job. Great job. All right, Chris, I'd like to have you introduce a question. Then we'll go to Alan to introduce Tariq, and then we'll finish it up by 18, 20 minutes after the hour. Chris, take it away. What's that question?
Yeah, so there was a great question on the question and answer about the increase of heat soak time during extreme cold weather fusion. McRoy saying in several scenarios that it could cause brittle fracture during destructive testing. So ultimately on that situation, if you're preheating your pipe properly, you shouldn't get to that situation where you're having a extreme case of heat soak time. So it's going to be the key of preheating your pipe before you make the fusion. So your heat soak times, yes, they're going to be extended, but they're not going to be that extended that it causes brittle pipe.
Good explanation. Thank you, Chris. Alan, you're up.
All right, very good, guys. There's a lot of different things to consider for cold weather fusion. And I have lived in Alaska before myself. One of the things that's always unique to me about Alaska is the conditions that are required to live in Alaska essentially create innovation just to be able to exist there. So many things become second nature and you continue to invent and reinvent. And we met Tarek last summer at a road show in Fairbanks. And I was just completely and totally taken with how many different things that they actually come up with for invention. Of course, necessity is the mother of invention, and to be able to live in Fairbanks in that, what would you say it was, already -40 there, Tarek? At some point in time, that's pretty cold. So you're living and breathing it. So without further ado, Tarek's going to share some of their story with us of how to actually use water systems in Fairbanks, Alaska.
Yeah, thanks, Alan. And boy, I sure wish I was part of this group 12 years ago when we started our journey. Would have saved a lot of mistakes. Can everyone see my screen?
I think we've got your presentation slides in with the main presentation. And right now we're looking at Fairbanks Sewer and Water Operations. Would it be okay?
I got you. So anyways, yeah, my name's Tarek Spear. Been working in water, wastewater design, development, and construction for 21 years. Fairbanks, we're located 120 miles south of the Arctic Circle. Sunrise this morning was 10:38 a.m. and sunset will be 3:20 p.m. And we have already been experiencing about a week of 35-40 below. Operating a water system in the Arctic environment comes with an abundance of challenges. Primarily, some of these challenges are large areas of our system. The ground will freeze 8 to 12 feet every winter. We call this seasonal freeze. We chart this ground freeze every winter by the month. And as you can see, this gray arc here, this is the roads, parking lots, areas where the snow's been cleared all winter. The frost drives its deepest. In late March, you can see frost depths of upwards of 12 feet, 8 to 12 feet. This yellow one is your yards, fields, back road or back behind easements behind properties that typically see 6 to 8 feet deep. So permafrost. Alaska is known for permafrost. It's ground that's just permanently frozen, very difficult for construction. I've seen water mains installed in this permafrost, and years later, they'll be installed at 4.5, 5 feet deep, and we'll find them at 13 feet deep. They just, as it melts, the mains tend to just settle out of sight. We've discovered directional boring of insulated jacketed pipe works real good because you don't disturb that upper layer. It tends to have a lot of heat built into it, and that helps protect the pipe from, anyways, it reduces the speed in which the ground thaws around it. Insulating costs, all of our system, most all our system has some form of insulation on it, depending on pipe size and thickness of material. This cost ranges from $10 to $25 a foot. I've been doing a lot of experimenting and testing on HDPE versus ductile, and some of the tests, the thermal loss tests, I'm finding I'm using 10-inch HDPE, SDR11, and 8-inch ductile, which tend to have about the most similar inside diameter and carrying capacity. That our typical construction standard for ductile is 2 inches of polyurethane foam. And with the HDPE, I'm able to get the same or better thermal heat retention with half of the insulation. So anyways, it's pretty exciting for us because insulation is a big cost. It's a big budget item when we're designing our capital and our projects. Labor, construction season in Alaska tends to run from March to October. This is probably an October picture. We have our heater set up, like Jim was explaining. This is a 8-inch HDPE main. We've had the luxury of a contractor here in Fairbanks that does polyurethane foam. They built a 40-foot lathe, and so they can take this 40-foot HDPE and place it on the lathe and uniformly spray on the exact measurement of insulation we want. So if we want 1 inch, this pipe would come with 1 inch of insulation, all dependent on how the water model and thermal loss calculations turn out on a loop and the speed at which it's going to lose its heat. Now, climate, this is probably a November picture. It's hard on people, hard on equipment. Water has to be circulated or glycoled. Equipment has to be preheated. This makes for a little longer projects, and not to mention daylight hours, like I mentioned. This is a SCADA view of one of our circ loops, and it kind of shows the thermal heat loss throughout a year. We spend about 640,000 in steam heat every year from a power plant to keep some of our outer loops at 36 to 38 degrees. You look, take December 23rd, 21, the ground temperature is still dropping, the water temperature is dropping, even though this main here is circulated at 100 GPM. It's about 64,000 feet of main, and it kind of flatlines around March or April, and then we have what's called the spring push, and that's around May. It seems like every year when the surface starts to thaw, that frost runs away from it and goes deeper, and so we'll see a drop in our water temperatures right around May. And then it'll start increasing again June, July, August, until it starts dropping again in late September. Circulation costs, power consumption. I always envy the gas and power and comm companies. They seem to be able to run infrastructure out 10 miles or 20 miles wherever they want and just end and start serving. Here in Fairbanks, if I run a new system, an expansion project, 10 miles, I have to turn around and either bring it back or, find other areas, subdivisions to pick up and hopefully amortize out some costs. But then I add a circ station and I run that circ station November through May. Most circ loops circulate from 100 GPM to 1500 GPM, depending on the volume of water. Corrosion, 4 out of 5 of the leaks we have in our system are corrosion holes, typically in a pipe called 10 gauge. We have a lot of that. The other 1 out of 5 typically is in copper service lines. So material handling costs. This project here was a 36,000 foot water project, expansion project, using the 4-inch SDR 11 insulated, jacketed with that jacketing I think Jim mentioned. We had that whole 36,000 feet show up on 4 tractor trailers. If that had been ductile, we're having material come from the manufacturer to a port, barged from the port to Alaska, would have been transported from that port to our insulator, insulated, and then transferred to the job site. This all showed up pre-insulated, jacketed, caps are on the end, offloaded, and went to work.
So Tariq, you mentioned insulated pipe. Do you use heat tracing on your insulation?
Some contracts require heat, you're talking heat tape, right?
Right.
Yeah. And so, yeah, we've done some force mains where there's a little channel installed and heat tape will be pulled through, but long-term, and I know I do want to talk to I can't remember his name a little bit more about it, but our experience with heat tape is, it's good for a certain period of time and then it quits working. So I'm interested in learning more about some of the better methods and materials that are out there. I haven't had much time to work with them, but most of what we do, like all of our water services, we run a 1/2-inch PEX to the main and back to the property. And then if the service freezes, we circulate hot water through that and it thaws the service out.
So you just
So-
run that PEX parallel with the polyethylene?
Yeah,
And
yeah.
how deep
slide-
is that polyethylene service line?
Typically about 4.5 to 5.5 feet.
So it's above the frost line.
No, it's in the wintertime, that frost in a lot of areas and parking lots and stuff and driveways will freeze 10, 12 feet deep. So it's in frozen ground. A lot of our system, we figure well over 75% of our system sometimes spends the better part of winter in frozen ground.
We still have quite a few people on the call and I've promised to get this thing done by 20 minutes after the hour, but I've got a couple other questions. You mentioned that you thought you wish that you'd met us earlier. You and I met each other this summer up in Fairbanks. What are the 3 biggest issues that you wish you knew that you know now that you wish you knew 10 years ago?
Oh, well, for one, the pipe handling, the staging, some of the other materials and equipment that are available through McElroy, some of the other piping products like this 36,000 foot water project that's on the screen here now. We built our own trailer for this. You'll see in the other picture to transport the 50-foot lengths of pipe, has drop down sides that we can roll onto the roller and put through the fusion process. Some of the engineering, but primarily just kind of the network of professionals to kind of sound ideas off of more than anything. And our standards, we're still working on developing sound standards. We have standards for a 3/4, 1-inch service connection. We have standards for main extensions, but there's still a lot of areas that we can improve our standards to give our customers and contractors other opportunities that would include HDPE pipe.
So are you doing your own installations or are you bidding it all out?
No, we do our own installations. 98% of our piping is put in-house. We did do a project last year where, we contract out the directional drilling. Every now and then there'll be a DOT project or something that'll use HDPE and like we had a 18-inch river crossing of the Chena River. That's done by a contractor, but overseen by us.
And are you using electrofusion, Tariq?
We're using, butt fusion and electrofusion. Yep. And have had absolutely phenomenal results with all of it. We've installed 7,800 foot project, 36,000 foot project, 64,000 foot project, 4, 6 up to 18-inch main diameters, thousands of feet in sewer force mains now. Lift station rehabs, and we've only ever had 2 leaks, and those were contractor damage.
So what kind of mistakes did the contractor make to get 2 failures?
Well, probably not using a number 2 shovel more and relying on an excavator bucket to find our main.
But so you don't have trouble with your electrofusion saddles?
No, now we did. So our first pilot project, WL Plastics actually did a little case study on it. And we were using the electrofuse saddles at that time. And then we were fusing on poly valves. We got away from that after that project because it was too time consuming. We went to Romac saddles with a corp stop and then a swivel by flare adapter by plane end. And so, it doesn't require the generator be there or the fusion machine be there. Because we can
Okay, so that's a mechanical connection with a corporation that then connects to polyethylene. right?
Correct. Yep. And
Yeah.
we can have the spool all pre-built on a trailer, and we bring it down and we tie on the swivel by flare adapters, and then we start rolling it out to the property. So at this time, there's no fusing, anything done at the saddle connection. So it
Yeah,
just
so
sped up when
Alan's
we were doing-
Alan's pulling that up nice and tight. So we can see that mechanical connection onto that polyethylene main. And then you've got the PEX warming coil that runs
Yep.
parallel with the polyethylene that has
Yep,
been
and then that's all
electrofused.
insulated in 3 inches of polyurethane foam.
Ah, wow. Fantastic.
And we,
Now-
and we have had 2 services freeze. We have hundreds of services out there now. And we've had 2 services freeze, and in both cases, the customer thought they'd save money when they went on vacation and didn't turn their circ pump on. And the thaw method worked perfectly. It takes very little time to circulate hot water through that PEX line and thaw out those 2 HDPE service lines. Because again, all of our mains are circulated and the services have to be circulated too. When that water stops moving, it freezes.
Well, I love the fact that it's working, but I'd recommend not using a mechanical, particularly within the frost line like that. Because after you retire, Tariq, that'll be the first thing to fail because it's mechanical touching the polyethylene. So I'd recommend to my audience anyway, take the time to use electrofusion because it really does work and it's never going to fail on you. So, but I have seen what Tariq is doing throughout the United States because it's more expeditious. It works and it works for a period of time, but it won't last as long as the polyethylene.
Yeah, and the electrofuse. So we were advised by the gas company here in the beginning too during that first pilot project. I'm not sure if there's gas folks on here, but we were told to avoid electrofusion at all costs because if you're going to have a failure, that's where it's going to be. Well, we've also done a lot of testing, and I'll tell you what, I firmly believe the electrofuse couplings, and I mean we're doing 14-inch. 18-inch. We have had absolutely zero trouble with any of them.
So I love you telling that story. So for our audience's benefit, what we've learned from utilities and municipalities like Tariq's that have adopted polyethylene in a major way, that if they do have failures, it's with an electrofusion saddle. Now, the gas industry has used more electrofusion than anybody else in the world, and they do it judiciously with proper procedures, and they rarely have failures. But when you compare a butt fusion to an electrofusion, in North America anyway, an electrofusion is initially more complicated because it has a couple additional steps. But in Europe, that's their primary fusion method versus butt fusion. So it's just kind of interesting, depends on where you come from. Now, Tariq, I want to respect my audience's time. One final comment on maybe a thing that you wish you learned, but you did a fantastic job today. And it makes me realize that we probably ought to do a case study webinar with you as one of our participants. Tariq, what else would you like to say today?
Well, I guess if in final closing, when I was a young operator and stuff, and I heard other operators, seasoned operators in the field, and the comment that was always made was, this will last until I'm out of here, and this will last till I'm out of here. This pipe repair, this pipe product, or whatever. And I just always thought, once I started working with HDPE, I mean, I want things to last 3 or 4 generations, 300 or 400 years. And I hope that, in 100 years or 50 years, when new operators are still doing repairs and this HDPE, we continue to have more of it installed, that, they recognize the value and appreciate the time that we put into starting this and using this. It's going to save the company. It's going to save our ratepayers. It's going to save our investors for years.
Yeah, well said. I love it. Thank you very much, Tariq, for putting that slide deck together and taking the time to spend with us on a webinar. And please contact us anytime with any issues you have with polyethylene, and hopefully you'll invite us back to Fairbanks next summer. I want to say thank you to Jim Johnston, Rick Ponder, Chris Waite, Matt Hahn and Richard Colassa on questions, and Aaron Davey and my team of Alliance Engineers. Stay on at the end and answer Dan Landy's question, and then you can get your PDHs or your CEUs depending on what your interest is. We'll keep the line up for about 5 more minutes because we've got a couple more questions here we haven't answered yet. So we will see you in February, the 7th and 8th in our next webinars. I want to say thank you all to our guests for hanging out with us here on this wonderful talk, Cold Fusion Weather Operations. Okay, bye for now. Answer the question at the end. Thank you so much.